Good morning, everybody. I'm very pleased to be here. I'm Sebastian. I have like two hats on. On the one hand, I'm professor for computer security and cryptography at Flensburg University. This is quite north of Germany, very close to the Danish border. And I'm also the CTO of enclaive, which is developing open source tools for confidential compute. And I have been in the space of confidential compute literally my whole business life. So everything started with my journey as a PhD. This is where, I went down the rabbit hole as a cryptographer in particular. And this talk is a bit like, a summary of my journey, how I ended up in what people call today confidential compute. So it's more like a high-level introduction to confidential compute, and my personal goal is to at least convince some of you that confidential compute might really be the next, say, software and development paradigm. This talk is a bit longer because a friend of mine, Arvid, unfortunately couldn't attend today, so I'm taking over also some of his slides. And if you guys have any questions, feel free to interrupt because, as Luca told me some minutes ago, we have enough time to discuss. And I think this is important because confidential compute is, as mentioned, a very cool paradigm, and I would really be happy if you also share this opinion after the talk with me. So let's start confidential compute. So people say it solves a 14 years open problem. At least cryptographers do that because Ron Rivest, VR and RSA, famously claimed more than 40 years ago, if we could compute on encrypted data, that would be magnificent. And confidential compute is solving this grand challenge of computing on encrypted data, as cryptographers would say that, with more an engineering and less than an, say, mathematical approach, which is typically based on complexity assumptions. Developers, on the other hand, would say confidential compute is a technology that for the very first time allows us to isolate applications from the infrastructure. Yeah? And this is, I think, also quite cool because it opens up a lot of opportunities how we can at least securely deploy the software we develop. And the nice thing is, and this is already something looking ahead, with confidential compute, literally we as developers have to do nothing. And for such a powerful security technology, say the performance overhead is almost negligible. And this is also sensational because we as cryptographers back in the days used to work with fully homomorphic encryption, multi-party computation, maybe you guys are familiar with the concepts. And whatever we tried to do had always a significant performance penalty. Confidential compute doesn't bring that. And for the rest of the talk, whenever I talk about confidential compute, what you always can try to think in your head is it's about creating black boxes. Black boxes or blind boxes. So we can put any code, any data in that box. Typically people call it an enclave. And whatever happens in that box is shielded and protected against the outside. And how that works technically, I'm going to tell about that later. But just bear in mind, black box, blind box, I'm going to use those terms interchangeable. Yeah, and here comes literally the only prerequisite in order to activate confidential compute. Yeah. We need standard CPUs. That's it. Yeah. So here is a list of processor series from Intel, AMD. ARM is also working on that. NVIDIA is working on that. There's also work in the RISC-V community. And the whole idea of confidential compute is take an existing CPU and put a security processor into this CPU. So it's somehow an evolutionary technology in comparison to TPM-based technologies. Leonard, for example, had a talk yesterday about TPM and Linux. We could also think that the security processor is like the next evolvement of TPM technology, with the difference that it's no more a standalone chip, but this power of the crypto processor is now on the SoC of a standard Intel, AMD, ARM CPU. And all we just need is, of course, a bit drivers, certain, say, software add-ons and kernels and so on, such that this security processor is enabled. That's literally it. And if we have that, the question is, of course, why do we need it? And I think the killer use case and also the timing is right for this technology. It's cloud. So everything is cloud. My hypothesis is, say, most of the software in the future will be deployed in the cloud. And we know that the cloud is about sharing resources, sharing infrastructure, and we also know that the way, at least clouds are architectures these days, leak workload by default. Yeah. So, for example, the cloud service provider, who administrates the infrastructure, sees everything what your workload is. And we can, of course, imagine that there are plenty of use cases, in particular in a world where AI, where data is like dominating. It makes sense to somehow shield your data, your workload, your code. Confidential computing comes to rescue here because with the help of that security processor, we can radically change our security model. Yeah. So, I mentioned before that, say, there are, say, two paths of the security processors. There is, say, the SGX path, which allows to enclave at the level of an application or a container. And then there are the other technologies like AMD SAF, which allow to enclave at the level of virtual machines. And through the enclavation, through the ability to create the black box, suddenly the security model changes, as mentioned. And what does that mean? What you see on the illustrations on the right, this is, a standard simplified cloud architecture where you, for example, have a host operating system, a hypervisor, and then you try to virtualize your workload. And say my whole academic career was always defined upon the assumption that you always have to trust your base. And the base is, of course, the whole code that runs underneath your application. But with confidential compute, we don't have to do that anymore. Yeah, because we create now an enclave, say, around a virtual machine. So this is something like a black box around the virtual machine. And anything underneath can be corrupted, can be malicious. Yeah? So I don't have to trust, say, the infrastructure provider anymore. And this is, I think, a significant breakthrough. Because as a security guy, I, for example, can now get a security solution, which, well, we will see later, is very easy to implement, gives, a lot of security, and protects my data without, for example, caring, do I have to trust the underlying host operating system underneath? And that was, as mentioned in the past, a fundamental assumption. Yeah. What does that mean concretely? For example, let's consider, the VM-based enclavation empowered through, say, Intel DDX or AMD Ceph, and let's consider a Kubernetes cluster. I could, for example, enclave now my node, put, say, my code into that node, run it as usual, and anything which runs, say, next to the node or underneath the node could be potentially corrupted. The technology just makes sure that whatever happens underneath or aside doesn't really impact the execution of my code, my process, my program. If we would even go further towards application or enclavation at application layer, like Intel SGX offers that, we could even shield our application at the level of a pod. So even if I, for example, run a cluster with multiple nodes and run maybe a single pod in the node, this pod would be shielded against neighboring malicious pods. Got it. Questions so far?
So your trust still needs to go somewhere. In this case, it's not at the software level anymore, but it's in the implementation of the security chip itself, right? So how can we sure that those vendors that are getting a monopoly, they don't have a backdoor implementation of a security chip?
Yeah, so it's a good question. People ask me a lot, and my argument, but this is my personal one, is today there is a fundamental say assumption of how we trust computing. Namely, it's the CPU, right? This is the only assumption we have to do. And think about we're running any fancy cryptographic algorithm, right? Even this algorithm needs to trust the CPU because the CPU is in charge for computing the mathematical operations. The CPU is in charge for rendering sampling randomness. So we're still relying on the trust of the CPU to provide the right micro instructions. And for security extensions, you could think about adding just 15 to 18 or even some more instructions into the architecture of the CPU.
That's true. I just wanted to say that you have it also on the slide. We don't always trust the CPU. You have Spectre, Meltdown that happen, right? So, and sometimes higher layers such as DOS need to work around problems in the CPU design, right? And microcode is also software at the end.
It is, right? And I wouldn't say that Meltdown and other, cache-based attacks are, say, purposely, implemented in order to leave a side bug. They are just as you said, right? Kind of software bugs which happen all the time and they need to be fixed, right? And another argument, maybe if this doesn't convince you, is there are, say, 2-3 great CPU vendors in the world. If one of them, turns out to be having implemented somehow a backdoor, right? This is definitely the end of that business because that market is so competitive. And the others are just waiting until one makes a significant mistake. And I think against this background, in the end, right, I mean, these are commercially driven companies. If they make that strategic move, they would ruin their business.
So before the next question, I have another argument, I think, as an Azure guy. So before this, you had to trust the CPU and Microsoft and AWS. With this, you just trust the CPU. It's not perfect, but it's much better. It's an argument I like.
So the one thing that I'm kind of curious about is, especially in this model where you are trying to protect the container is at least in the current way of programming things, inherently doing all sorts of syscalls. So, for example, if you take a project like gvisor, but you make a malicious version of that, that intercepts your syscalls, what's there to stop anything from doing that? You've still got to essentially trust your infrastructure provider not to be completely malicious. Unless you're proposing that we're basically executing a second kind of kernel thingy within the enclave that can also do all kinds of I/O.
Regarding I/O, there's ongoing work how to also secure the communication. For example, AMD recently published TIO, Trusted I/O, that goes a bit in this direction. And where I definitely are with you is the fact that whatever we put now in the enclave, of course, is not our responsibility. Yeah. For example, if we consider the VM-based enclave and we put, say, a full-fledged, non-verified, guest operating system with, I don't know, a kernel no one has scrutinized so far, then it's somehow our responsibility if that code is malicious, if there are backdoors. Yeah? But my point is that, this technology has always to be adjusted to the use case, right? And for, say, high security use cases, maybe you really want to have the TCB as small as possible of that enclave, so SGX might be the right choice. But for a lot of applications, you're just fine with, controlling what is in your VM, yeah, because, you have a lot of universality, generality, and ease of use with that approach. And this way, for example, always, somehow, balance the security versus, say, performance and usability you want to have. This has been always something like the trilemma, in my past whenever I came up with security innovation. Yeah, got it. So I think now is a good moment to give you guys a small demo, because I personally believe always that seeing is believing. Yeah. So I created, with a team some videos. You can go to our YouTube channel at Confidential Compute, or through GitHub. You're going to find the link to that, where you have created a series of demo videos how enclavation technology works. I'm now going to show you two examples. One example is Redis. Redis is in-memory database, and what we want to see is that we're going to do a memory dump of Redis after writing a key value into the database, and then we're going to do the memory dump, and in the non-enclaved version, of course, we're going to see what we entered. In the enclaved version, we're not going to be able to see what we wrote before. Yeah. So for the orientation, the terminal to the left, bottom left, is the enclaved Docker container of Redis, and to the right is the non-enclaved. And as mentioned, we're just gonna we're gonna start the two containers, and then write just a key MySecret into the databases. And then once we did the memory dump, we're going to search for the string MySecret, and hopefully the magic that we're going to see is going to be convincing. So this is a process ID. We searched for let's see whether this is better. Exactly. So in the dump, there was a match. And now let's do the same with the enclaved Redis. Yeah. So process ID is 9122, made the dump, and now we're going to search for the string my secret, and we see there is no my secret because it's a ciphertext. Yeah? So everything what runs in the memory is like encrypted, so whenever we do a memory dump, we just get ciphertext, so we cannot search for the plain text my secret anymore. Another example which goes also hand in hand with the technology is, of course, integrity protection. And the second example I now want to show to you guys is about a very simple Hello World kind of C# application, which reads from a file. Yeah, it's like a Hello World, and in this file, there's a paragraph from Shakespeare. Yeah, and we're gonna repeatedly print out the text paragraph, and in the attack model, we want to modify the text on the fly. So we're gonna try to modify the file on the fly, and the non-enclaved program will allow the modification, so we can change the Shakespeare text. The enclaved execution will prevent that. Yeah, so starting the write, the non-enclaved. So now we're attacking the non-enclaved container, and we see we could inject a bad string. And now let's try to see what happens when we do it with the enclaved container. Yeah, the container execution aborts. And the reason for that is that the integrity protection, the enclavation mechanism, just figured out that there is some bad hash value, and because of that, the whole enclavation execution detected that and stopped the process. So the whole idea is to just show that we can not only achieve the confidentiality of an enclave, but we can also safeguard the integrity and the authenticity of the code which runs in the enclave. That's the magic. I hope that those examples haven't been too fast, but if you just want to reproduce them, as mentioned, go to YouTube, go to GitHub, there is the whole code, there's the demo code, you can just reproduce everything. Cool, so if there are no further questions, I'm going to go over to the next part, which is a bit more technical. How does it work? Irrespectively, whether we're now talking about enclavation at the container level or enclavation of the VM level, the concepts I'm going to now present to you are universal to both of them. The details of the implementations vary, of course, also to the security extension you use, but the high-level concepts are similar. And from a technical point of view, an enclave, this black box or blind box, is realized for something that we call 3D encryption. And 3D encryption stands for data in transit encryption, data at rest encryption, and data in use encryption. So, putting in other words, we need to 3D encrypt, say, our process in order to get the claimed security of an enclave. Data in transit encryption, I think this is something I'm not going to dive much deeper into. It's about how can I establish a secure communication channel into the enclave. Typically, we do it via SSH or SSL/TLS. Yeah. Data at rest encryption changes a bit because data at rest encryption, for example, is implemented for disencryption in VMs. And a similar concept now comes into the game. But it has to be modified slightly through some special protocols, simply because we have to make sure that the key in order to encrypt or decrypt the disk is securely provisioned into the enclave. And data in use encryption is then, say, the topping, which is realized through memory encryption. Yeah. And how can you guys, imagine memory encryption? So what you see here is also a very simplified view. On the right, you see a CPU architecture, which 10 minutes? Okay. Okay. A CPU architecture consisting of an ALU and a memory management unit. And on the left, there is now this extra superpower through the security processor. And think about that. There is an AES engine available and a secure key storage mechanism. Yeah. And what now happens is whenever we, for example, retrieve from a memory a micro-instruction, this micro-instruction is decrypted, executed through the ALU, then re-encrypted before it's written back to the memory. Yeah? So just think about an encryption-decryption unit is in between the CPU and the memory, and it's on the CPU dice. And all now the CPU needs to know, and this is where the operating system typically helps, is to understand that, hey, this micro-instruction comes now from a memory area, which is specifically reserved for enclave processes, versus it's coming from a memory area which is not reserved for enclave processes. Yeah? And this is where, some say, magic or some support with an existing Linux kernel is implemented to just help the CPU to understand where does this micro-instruction come from and is it encrypted or not. Then another novelty of the whole technology is those enclave applications have now an identity. Yeah, so we can really now authenticate the workload. And this typically works by using a feature which is called attestation. And the CPU has now the extra power that it can measure the process. And through the measurement, it can now issue certificates, and those certificates we can now use to send out to other services or other parties and authenticate the process or the code running in the process. Yeah, and this concept is quite similar to attestation back in the TPM specification. Yeah, it borrows the ideas. Yeah. What we also need to understand that if now workload has identity, we can use that extra information in order to define certain access policies. So think about now you have an external service. It's like a workload identity management service, which asks the CPU, please tell me, say, what is, say, the signature of that process, enclave process. It can be a VM or an application. And once you have this identity, you typically use a key provisioning service. So a service which has now, for example, the disencryption key for your volume stored. And you first of all check the identity of the VM. If that matches the reference values, you then tell the key management service, please provide the disencryption key into the enclave. And then this encryption key provisioned in the enclave could be used in order to decrypt any encrypted volume, for example, through looks or similar tools. Yeah, and these are the core concepts. Yeah, any of the confidential compute hardware providers needs, and that you effectively have to implement if you want to build confidential workload, for example, in the cloud. Yeah. Got it. Questions so far?
Yeah, so I'm not sure if that makes sense, but from the picture with the security chip next to the CPU that sort of acts as a decryption encryption mechanism between the CPU and the outer world. So that one. Does it mean that the application that's actually being executed needs to understand that it's running in an enclave and do some special setup to do that, or does that work out of the box?
So what we need to do is to somehow encode in the application some kind of, I call it a bit, telling literally the CPU this is an encrypted application or not, or an enclave application or not. Yeah. And now, if you ask how you do it in practice, if you go for SGX, of course, you have to take your application and put some extra around your application in order to turn it into an enclaved, binary. In terms of enclave virtual machines, you don't have to do nothing because your VM by default is already started in such a way that your CPU knows whatever now happens in that, VM memory space has to be encrypted by default.
So it's kind of in the VM case, it's sort of the most enclosed host system that sort of deals with that, or?
Yeah, you can say so.
Thanks.
Thank you for the talk. I find it really interesting. I've been running a lot of systems, just because I'm very paranoid, and I hope I can stop this,
is your
very
technology.
soon. So I have the question, how is it regarding performance? What are the implications? And if I understand remote attestation completely, could I, for example, ask, is the container running in the enclave just defined by my Docker file and nothing else? Very practically.
Yeah. It's like that. So let's start with the most interesting question, performance. So going back to the table, we have two different paths, and SGX, the mother of confidential compute, started 2015, first approach, how to, enclave applications. This is great if you want to have a small trusted computing base, but the way you typically enclave an existing application is by wrapping it into a libOS. Are you familiar with the concept libOS? Yeah. So you wrap it because you would like to have, standardized interfaces that allow you to just enclave any application. And the way libOSs work, there are also a lot of approaches, but for example, those that have been tailored for SGX technology try to be as lean as possible, but this means that they use a lot of kernel functionalities in order to answer the syscalls. And whenever there is, a swap from the enclave process to, the kernel process, there is this performance bottleneck. Yeah? And because of that, SGX has, a performance overhead, from 1 to 20x. Yeah, depending, and the answer is depending on what kind of syscalls are needed and how many are needed. Yeah. Then with SGX, certain applications, for example, are not enclaveable at all. For example, Postgres, because Postgres uses shared memory. And the idea of shared memory conflicts with security model of SGX because you really want to have, say, your enclave process, and it shouldn't talk to another process which shares any resources. Now, on the other hand, comes the VM-based approach, and Ceph is currently publicly available. TDX is something we are now previewing with Intel together, but there are little differences. Ceph, on the other hand, has a performance overhead of at most 2% of CPU cycles. 2%, yeah, at most. Yeah. TDX is around, say, 4 to 6%. Also, of course, depending a bit on applications and so on. But long story short, if you consider, say, cloud-based applications, and you, for example, trust, say, your trusted computing base you put into the VM, my recommendation is go for enclave VMs and do it already now, because there is no performance overhead for you right now. Yeah, so you have a VM, and a VM works, a confidential VM works like a non-confidential one. You just SSH in, you put whatever you put into your VM, and it works like before. No wrapping with libauthors, no pre-compiling, no going an extra mile. It works out of the box. Yeah. No performance overhead. The only thing which is currently happening is that hyperscalers, because they are the first that now offer, say, Ceph-based and soon TDX-based compute, they of course want 10 to 20% more for that superpower. But we, for example, work with Berlin-based cloud provider Crowd. You literally get the same machines for 50% of that of hyperscalers. Yeah. So if price is in the end a reason. Yeah. So the decision now you have to fell is: am I super paranoid? So do I need a small trusted computing base, a small footprint? Then SGX, but bear in mind that performance might be growing. If you guys wanna try that out, go to our GitHub, because we created like 18 out-of-the-box ready Docker container, like Maria, Redis, Python, C#, whatever you need in order to build a cloud application. They are already the ready applications, and you can start working with that. Otherwise, go to one of the hyperscalers, book a Ceph-enabled virtual machine, and get going. Yeah. Now your second question, attestation, is now an important thing, because you really want to figure out, is my workload now really running in an enclave? So there are two ways to go. Either you take, say, the attestation services that hyperscalers already provide, both for SGX and Ceph, there is something in place. Yeah. Or you do, say, you use external services. For example, we have implemented Vault, we have implemented Nitrite with effectively our open source component that literally allow you to run your attestation and key provisioning mechanism wherever you want. Yeah, you could, for example, think of, hey, I would like to have my key vault running maybe on my on-premises, yeah, or in my trusted zone, and then just use the compute resources running in an enclave from the hyperscaler. And this is also a bit the direction we from Enclave work towards. Yeah? Because if you understand the concept of confidential compute, yeah, the future is now we have compute, it's enclaved, so I can run it literally anywhere I want. Yeah? So think about this super duper vision of multi-cloud computing, but now you can really even run on environments in maybe less hyperscaler dominated data centers. Yeah? You have all liberty. Yeah? All you just need to do is key management and workload identity management. This is the key components you have to rather trust, maintain, and make sure that it's somehow in your trusted belly. Yeah? And then compute becomes just a commodity. All right, I think.
Yes, I think that is it. So let's thank Sebastian. Thank you.
Thanks, guys.